Hello, everyone. Welcome to another Math Divulge lecture. Today, we'll be talking about conics, conic sections, which are really important for math and your math classes in the future. So let's get excited. So I'm Benjamin Wright. I'll be your teacher for this class. Your teacher assistant will be Dylan Liu. Please direct all questions during the course of the class to him. I'll be too busy teaching to answer them. Okay. Okay, so there are many ways to define conic sections. The way we're going to start off is the geometric definition. And that involves having a focus and a directrix. Oh no, those are fancy words, but all that means is that we have a point and a line, line, and we pick points based on the lines. So the way we find the conic section from a point and a directrix, let me draw it in this middle section here. We find all the points that have the same ratio between the distance to the directrix and the distance to the focus. So we're looking at these two segments I drew. So looking at this ellipse, the red to green lengths, these ratios are the same for every single point we pick. The red lengths and the green lengths don't equal each other, but the ratio of red to green is the same. And this is true for all of these shapes. So the ellipse is when this ratio is less than 1. We have the parabola over here to the right, and that's when the ratio equals 1. We have a circle when the ratio equals 0. And then we have a hyperbola for when the ratio is greater than 1. Okay. So this is the initial way we're going to define conic sections. As like we have a point, a focus, we have a line, the directrix, and we have an eccentricity, which is the ratio of the distance to the focus over the distance to the directrix. Okay. So that's definition 1. Which is this to focus. There's a second definition for conics, which is the one you might have encountered before. And this is the algebraic definition. If you plot conics on the coordinate space, you'll see that they look something like this. You have an x squared term, you have a y squared term, maybe you have some linear x and y terms, and then you have a constant. Any shape that fills these criteria can count as a conic section. Like the only exceptions are when these two terms are both 0, then we just get a line, or sometimes even a point. And lines and points are degenerate. So they don't actually count as conics most of the time. Most of the people you ask will say lines and points are not conics. So as long as you satisfy this algebraic equation and you have at least one quadratic term, one x squared or one y squared, then you're fine. So I'm sure some of you know the equation x squared plus y squared equals r squared. This is an equation of a circle with radius r. And as you notice, this equation fits that. I'll be going over the more complicated algebraic definitions for conics later on. I think I should go through the conic sections one by one. So I guess I'll leave it to the future. Anyway, these are the two most common definitions for conic sections. Okay, let's get on to our first conic section. So the circle is the most basic one, but you guys already know what circles are, hopefully. So I'm not going to go through that. Next one is the ellipse. Okay, the ellipse. So ellipses are when you have a ratio or an eccentricity less than 1. So for example, let's just say the eccentricity is a half. Then this point would be on the ellipse because the distance to the focus, the screen length, is half of this distance to the directrix. So that's what eccentricity half means. And if you follow all the points that have this half ratio, you get something like this, probably. Yeah. So this is how you get an ellipse. Now, one of the nice things about ellipses is that they're actually symmetrical. So we took this point as a focus, but we actually could have taken the opposite point as a focus. And we could have used this as a line instead. So when you have the ellipse, there's actually 2 possible directrixes and 2 possible foci. And we can actually use this to find out more properties about ellipses. Okay. So I'm going to call this green length x. I'm going to call this length y. Let's not do that. Okay. Some of you may have learned ellipses before, and you'll know that there's actually another definition of ellipses in particular that's often taught as how you first define ellipses. And that definition is if you take a point and you sum up the distance to the 2 foci, you'll get a constant. So pf1 plus pf2 equals a constant. And this will be how you how you draw an ellipse in real life. You would get 2 points and you would get like a rubber band, and you would just stretch the point along. And you can form an ellipse like that. But how do we prove this? How do we prove this? Well, we can prove this using our focus definition. So we know that PF1, we can relate PF1 to this length over here, one half PD1. Because we know that the eccentricity is a half. But we can also relate the other side to this length. Because we know that there are 2 foci, instead of using this foci, we can instead use this foci. So PF2 is 1/2 PD2. So if we sum them up, what do we get? Summing them up gives us PF1 plus PF2 equals 1/2 PD1 plus 1/2 PD2. And the important part here is that D1, D2 is just the length between these 2 parallel lines. So PD1 plus PD2 is actually a constant. And this shows that PF1 plus PF2 is a constant as well. So that proves this golden statement down below. Now, I used 1/2 here. Let me circle all the times I used 1/2. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. These 1/2s can be any number between 0 and 1. That's the eccentricity. So normally this 1/2 will be replaced with a little e, denoting eccentricity. But the proof is still the same. I think this proof is pretty cool. Okay, what else? Okay, more about ellipses. So in an ellipse, you have 2 axes of symmetry. There's this long axis and there's this short axis. And we can actually define lengths based on this. This length is denoted as little a, and this length is denoted as little b. It's always a and it's always b for convention. And in this case, the formula of the ellipse is x squared over a squared plus y squared over b squared is equal to 1. This is the formula. Can you guys understand why this is the formula? Oh, am I lagging? Oops, this is bad. Am I lagging? Can you guys hear me? It's good now? Okay. So once again, I just want you guys, do you guys understand why this is the formula? Why is this a formula? You don't need the Pythagorean theorem for this formula. I mean, I guess maybe. Okay, so there are two ways to derive this formula. One way is, if you assume that this is the origin, then I define the lengths as a and b. So this length must be a comma 0, and this length must be 0 comma b. So if you look at the, algebraic formula, a constant times x squared plus a constant times y squared equals a constant. This is the generic form how do I explain this? I think it's easier to just explain as, if you have a squared over a squared plus 0 squared over b squared, this is just by plugging a comma 0 into the formula. And as you can see, this is clearly 1. If you plug in 0 comma b into the formula, you get 0 squared over a squared plus b squared over b squared equals 1, which is true. So you guys, so you don't have to remember the formula. You should just remember how to derive the formula. Okay. So the formula, like to find out the formula for the ellipse, you just plug in the x-intercept and plug in the y-intercept, and it should give you like the equation pretty easily. Okay. So there's actually more stuff about a and b we can learn. For example, when we know a and b, where's the focus? Where's the directrix? Well, we can actually find them out in terms of a and b. The way we're going to do so is, if we mark focus 1 and focus 2, and we mark the x-intercepts as x1, x2, we know that pf1 plus pf2 is a constant for all points on the ellipse. So if you plug x1 into this, we get x1p. Oh, sorry. You get x1 f1 plus x1 f2 is the constant. But what is x1 f1 and x1 f2? Well, this is x1 f1, but x1 f2 we can actually put here. And that's because x1 f2 is equal to x2 f1, just by symmetry. You can just reflect it to the other side. So therefore, this equals x1 f1 plus f1 x2, which is just x1 x2 which is 2a. So the constant P1 F1 plus P F2, this is just always equal to 2 times a. Okay, so far we've derived this. Now back to the ellipse. Okay, so now we need to, now I want us to find how far the focus is from the center. This point is a comma 0, this point is 0 comma b. So before we plugged in x1 and x2, so now I'm going to plug in y1 and y1 or y2 here. So if I plug in y1, we get f1 y1 plus f2 y1 is equal to 2a. So f1 y1 and f2 y1 are equal. So this tells us that f1 y1 is equal to a. If we mark this length, we have an a here. But we also know by definition that this length is b. So therefore, we have a right triangle. We have a hypotenuse of a, we have a leg of b. So therefore, the origin to f1 is square root of a squared minus b squared. You use Pythagorean theorem. And by convention, we just call this length c. So the origin to f1 is c. Okay. Okay, next step. We found out where the foci are, but we need to find out where the line is. Remember, there's this line called the directrix. So how do we find out how far this line is? Okay. So we know the definition that Pf1 over P to the directrix. I don't know how to write it in notation, but we know that this is a constant, which is equal to your eccentricity. So we don't know what the eccentricity of the ellipse is yet, so we can't just plug in 1 point. So we will have to plug in 2 points. So once again, we'll plug in x1 and x2. So plugging in x1 means x1 f1 over f1 d is equal to e. I just defined point d right now. Okay, and if you plug in x2, we get x2 f1 oops, my bad. This is x1 d. If you plug in this, we have x2 f1 over x2 d is equal to e. Okay, so our goal is to find where d is. So if we divide these two, we get x1 f1 over x1 d is equal to x2 f1 over x2 d. Okay, we actually know what some of these lengths are. We can replace x1 f1 with a minus c. That's because this whole length is a, but the smaller length is c. So if we subtract out the c, we get a minus c. A2F1 is similar, but instead of a minus c, we have a plus c, because we have a over here and we are adding c to the left of it. Now, x1d is the troublesome part. Here we're going to have to define a variable d, like little d. And then x1d is 2a plus d. Well, x2d is just d. So if we expand this out, we have d times a minus c is equal to 2a plus d times a plus c. I think, right? Oh shoot, okay. My bad, I made a mistake. I've been using F1, and the focus F1 needs to be with this directrix. That's because the left focus corresponds to left directrix, right focus corresponds to right directrix. So that means I mixed up these. This is D, this is 2a plus D. Okay, and if we solve it, we get D times 2c. We get D times 2c on the right, and on the left, we have 2a squared minus 2ac. So D is a squared minus ac over c, which is a squared over c minus a. So we have a squared over c minus a. Now, this doesn't seem like that nice of a number, but if you add on a to find the distance from the origin, this minus a, it vanishes. So we end up getting the directrix is just x equals a squared over c, or x equals negative a squared over c, depending on which direction you pick. Yay. The only important condition to note is that if the height is actually longer than the distance, then your A will be in the vertical direction. Sorry, your C will be in the vertical direction. Yeah, and your A. So you'll have 0, A and B, 0. And then your directrix will be y equals a squared over c instead. So just take into account that when it's taller than it's wide, you flip all the x and y stuff. Yeah, I think we've calculated everything. Yeah, we found the focus, we found the directrix, we found the sum constant. Okay. So we're done with coordinate algebra for now. Let's get back to some cool geometry about the ellipse. So we have our two foci. What we're going to look at now is tangent lines to the ellipse. Let's say this green line is a tangent line. Here's our focus 1, focus 2. So theorem. Line L is an external angle bisector of PF1, PF2. All this means is that these two angles are equal. So how do we show this? Before we show this, isn't this just like a cool fact? Like whenever you draw a tangent line, you can always just draw these two lines and you get two equal angles. I think it's pretty cool. So proving this. So the way we're going to prove this is, we know that PF1 plus PF2 is a constant, which is 2a. P is this point on the ellipse. So I guess what we're going to try and show is that P is the only point on the line satisfying this. We want to show WTS is my abbreviation for want to show. We want to show P is the only such point on line L. So how are you going to do that? Well, it seems pretty troublesome to just pick another line on this point and calculate like QF1 plus QF2. That's like, you can do that with coordinate algebra, but it's kind of annoying. So instead, we're going to do this cool thing where I drop an altitude and reflect this point F1. So this is like F1 star. So now that I reflected this, can you guys see where I'm going with this reflection? So the cool thing about reflecting over a line is that you don't actually change the distance. So F1 to P is actually the same as F1 star to P, as long as they're reflected over. So when we have PF1 plus PF2, we can reflect F1 over instead. Now we have this cool situation. We have this green line. We have a point F1 star. Sorry. Wait. We have a point F1 star. We have a point F2. And we're trying to find the sum of P to the two foci. So before we reflected, this point such that these angles are equal actually becomes the point such that P is on the line. So if you look at this point with equal angles, point P, then since it's on a straight line, we know that the straight line is the minimum distance. So if you pick any other point here, then the sum of like those two lengths is like either greater or like even way greater than the length from P, because a straight line is always the shortest. That's an axiom of geometry. It's something we assume. So you can actually have a second point. So if you remember what we're doing, we had an ellipse, we took a point P, we had these two focus lengths, and then we draw a line such that these two angles are equal, and we're trying to show that this line is tangent. So if this line weren't tangent, it would intersect at a second point, Q. And let's say that second point, Q, is here. But we know that if Q is on the ellipse, then QF1 plus QF2 must be the same length. But clearly, QF1 star plus QF2 can't be the same because it's not a straight line, so it must have a longer distance. So therefore, P is the only point on both L and the ellipse, which is enough to show that L is tangent. And that completes the proof. Yeah, apologies for if I was lagging and you can't understand. Hopefully you can understand the proof by reading, or just ask Dylan a lot. Should I spend more time to re-explain this, or are you guys good? Dylan is on. Okay. No one's saying anything. Wait, no. Okay, Dylan says he's not getting questions about this subject, so I guess I'm just gonna move on. Okay. Okay. So another definition of the ellipse is the smushed circle. And what does this mean? Well, it means that we take a circle, and for every point xy, we turn the point xy to x, and then a constant times y. Like we can just say 1/2 for now. Then all the x coordinates are the same, but suddenly, since all the y coordinates are just halved, you have this like smaller circle. We have a circle, and we just decrease all the y coordinates. So for example, if you drew a circle, but the y coordinates and x coordinates have different scales, then this would technically be a circle, but it looks a lot like an ellipse. But the visual shape is an ellipse. So you can actually make this constant any constant. So for example, if you make xy to like x, 3y, you would still be an ellipse. It's just that it would be like a vertical ellipse rather than the horizontal type ellipse. Okay. So how do we use this? Well, this Smushed circle definition is actually very useful when we want to calculate the area of the ellipse or the slopes of certain tangents. So let's first start with the area of the ellipse. So if we graph the ellipse and we have lengths of A and B, well, we can just consider this as a smushed circle of radius A. And this is a circle where x, comma y was changed to x, comma b over a y. So what this means is that if we take a very small rectangular segment of the circle, and that same rectangular segment for the ellipse, the area in the ellipse, this gold segment, is equal to b over a times the entire red segment. Yeah, this kind of looks like a sphere. I'm just drawing like a circle and an ellipse inside of it. So we know that the area of the ellipse is just a sum of a bunch of really small rectangles. So like if you want to find the area of the ellipse, we just take a whole bunch of these like rectangles side by side. And if we take enough rectangles and we take the bottom rectangles too, eventually we get the area of the ellipse. But we know that these rectangles are just b over a times the sum of the red rectangles. So that actually just gives us b over a times circle. So to find the area of the ellipse, we just need to find the area of the circle and multiply by b over a. So the circle area is pi times the radius squared, which is pi times a squared. So the ellipse area, we take b over a times the circle area, which is pi ab. So yeah, that's the formula. And this should be pretty intuitive because we know that a circle is actually technically an ellipse. So in a circle, a and b will be equal. So in a circle, you'd have pi times the radius, which is pi r squared, which matches with the area of a circle. So with an ellipse, you just do pi times one direction times the other direction. So that's the area. If you want to find the slope of a tangent line or the equation of a tangent line, all you need to think about is that the tangent line at the same point to the circle intersects at the same x coordinate. So to get from the circle to ellipse, we did this process where we multiplied every y coordinate by b over a. When we talk about tangent lines, that same phenomenon happens. We multiply every y coordinate of the tangent line by b over a. But we realize that this x coordinate, it has a y coordinate of 0. This would be like some constant comma 0 or something. We don't know what the constant is. But 0 times b over a is still 0. So the gold tangent line to the circle and the green tangent line to the ellipse, both have the same x-intercept. So that means that if you calculate the equation of the gold line, you can get the equation of the green line very easily. Okay, we're running out of time, so I'm not going to go over exactly how you do that, but this is the process of finding the tangent line. If you don't want to use calculus, you just use the Smushed Circle definition. If you have questions on that, go ask Dylan. Okay, that's it for ellipses. Let's go into parabolas. So parabolas have eccentricity 1. And what that means is that if you have the focus and the directrix, you look at all points that are equal distance from the focus and the directrix. So this is what a parabola will look like. And no matter the point you pick, these two distances will be the same. Okay. So the equation of the parabola will be something like y equals ax squared plus c if it's centered around, if there's no horizontal shift. If you add some horizontal shift, you can get y equals ax squared plus bx plus c. And this is a parabola that goes upwards. So what's special about this? Okay, there's a lot of stuff about parabolas. A cool similarity it has with ellipses is a special thing about the tangent line. If you take a tangent line at this point, guess what? If these two angles are equal. So similarly, we have tangent line bisects focus line and directrix line. I don't know what to actually call them, so I'll just call them focus line and directrix line. Okay, what's the proof of this? Well, let's call this point down here D. So we know that PF is equal to PD. So the angle bisector of PF and PD is actually the same as the perpendicular bisector of FD. So angle bisector is equivalent to perp bisector of FD. So what we're going to do is we're going to draw FD, and we're going to define this green line to be the perpendicular bisector. And we're going to prove that it's actually tangent. Okay, so the way we prove a line is tangent, similarly to what we did with ellipse, is we assume there's a second point of intersection and then prove that that second point of intersection can actually exist. So there can only be one intersection, which is the definition of tangent. So let's say that our line somehow is squiggly and intersects this point Q. So just from looking at this line, you know that there's no way it can intersect this point Q. It has to be tangent. But let's prove that. So Q is on the perpendicular bisector of FD. Q is on perp bisector. And that tells us that QF is equal to QD. all points on the perpendicular bisector are equidistant from those 2 points. So this blue line and this blue line are the same. But we also know from the definition of the parabola that Q to the focus must equal Q to the directrix. Let's call this point like E. So QF equals QE. And now here's our conundrum. We have QF is equal to QD, which is equal to QE. But clearly, QE and QD cannot be the same because QD, by the Pythagorean theorem, is QE. It's a bit more than QE. So this can't be true, which is a contradiction. So a brief summary of what we did again. If we define the green line to be the perpendicular bisector of F and D, we can show that it only has one intersection and is therefore tangent at P, because if there is a second intersection, we get a contradiction from the definition of the parabola, the focus definition of the parabola, and the definition of the perpendicular bisector. We get contradicting stuff. So the thing is, ED can't be 0 as long as Q is not equal to P. Like E and D are both like altitude, dropping in altitude from P and Q. So since P and Q are different, E and D have to be at different locations. Okay. So that's the cool tangent stuff for parabola. So there are different ways to write a parabola algebraically. So you've already seen y equals ax squared plus bx plus c. If you get rid of horizontal shift, you can also do this. A equals x minus h squared plus c. So this is removing the shift. And then there's this important formula, which is 4p times y minus k equals x minus h squared. Now, this is a formula you guys need to remember. You can derive it on your own, but we don't really have time for that. So this is the formula where h comma k is a vertex. The vertex is this bottommost point. And p is the distance from the vertex to the focus. By the definition of the parabola, this is also equal to the distance to the directrix. Okay, so write this formula down or something, or you can just Google it later. That formula will come up. I recommend you find some practice problems to write the formula of a parabola, but that's just, practice work. You'll probably do enough of that at school. Okay, moving on, hyperbolas. So hyperbolas have equations x squared over a squared minus y squared over b squared equals 1. Remember before, ellipses have the same exact formula, except this minus would be a plus. So hyperbolas are literally just an ellipse, but you change a plus to minus. What they look like is they have two asymptotic lines. And then your actual curve will start at a point and it will approach those lines. So this is what a hyperbola looks like. So once again, there are two foci. And hyperbolas are very, very, very similar to ellipses. So to be honest, I could just go through the whole same thing I did with ellipses, except we just have a minus like the whole time except for a plus. However, that would kind of be a waste of time. So I'm just going to list out the facts and you can prove them essentially the same way you did with ellipse. So if you have a point on the hyperbola, the hyperbola can be defined as PF1 minus PF2, taking the absolute value as a constant. This is the same as ellipse, except once again, you change plus to minus. Also, if you want to find the asymptotic lines, so to find the asymptotic lines, you take the equation and you modify it a bit. So you get rid of the 1, you change the 1 to 0. So when x and y are really, really, really large, the 1 is not really as important. So although I'm writing equals 0, it's more like it's approximately equal to 0 when x and y are really, really large. So when x and y are really, really large, you have x squared over a squared is approximately y squared over b squared. And if you take the square root, you have x over a is approximately y over b. So that tells us that these two lines are y equals b over ax and y equals negative b over ax. So that's how you get the two lines. The slopes are a over b. Now, if you remember, to find the formula of the ellipse, I just told you to plug in the x-intercept and y-intercept. If you do the same here, we can find out the coordinate of this point. It's actually a comma 0. And it must be a comma 0 for this equation to be true. So a is this length. Now the next step is to draw a box. So if I can draw the same box out here, just a bit bigger. So from the center, you have A length, we have B height, and we have C diagonal here. So just like the ellipse, we have C, A, and B in the Pythagorean triple, except now C squared equals A squared plus B squared. So C is this diagonal. If you remember, C was the distance from the origin to the focus of the ellipse. Here it's the same. C is also equal to OF1. So if I draw these two lengths, this green length, which is C, is actually equal to this green length, OF1. They don't look very the same, but they are the same. What else? Okay, I think I've got everything for hyperbolas. Yeah, the most important part is the box. Just remember the box. You have A is half the width, B is half the height, and C is half the diagonal. And C is the length from 0 to the focus. Okay. So that's all the properties of conics I'm going to go through. To end, I'm just going to show you some cool pictures to give you another understanding of what conics are. So here you go. This is on Wikipedia. So this is like a GIF. So this is showing if you have this red point as the focus, and you have the eccentricity slowly increasing. At 0, you have a circle, and as you increase, you start to become an ellipse, then you get a parabola, and then you get a hyperbola. So that's just a drawing. Hopefully it helps you understand conics a bit better. Just one GIF. You can find on Wikipedia. Another important picture is this one. So conics are called conic sections. And the reason why they're called conic sections is because if you have two cones like this, all the conic sections can be formed by taking cross sections. Hence, you have cones, cross sections, hence conic sections. So 1 shows you the parabola, 2 shows you ellipses and circles, and 3 shows you hyperbolas. So with this final picture, I'm out of things to say. Hopefully you've enjoyed learning about conic sections. They're really important. You guys should do practice problems, understand this more. Thank you all for coming. Well, if you have any other questions, you can stay afterwards, but that's it for me. See you guys later.